Question 2 is on nucleophilic aromatic substitution with benzene rings. And another way of saying that is SNAR, which is what is said in the question. Now what they're telling you is you have 3 different rings, and each of these are going to undergo a reaction with KOH. And all that means is you have OH minus attacking these rings somewhere. Now, what you first have to do is recognize, well, which kind of SNAR reaction is this? Is this addition elimination or elimination addition? So starting off, we have a base. We also have a good nucleophile, but which one is it? If it's not NH2 minus, typically it is not as strong a base. OH minus is a good base, yes, but it's not nearly as strong as an N minus. And so we have an okay base, and we're reacting it with rings that have leaving groups and withdrawing groups. NO2 and chlorine are both withdrawing groups, although NO2 is a much stronger withdrawing group. So for that reason, I'm going to say that this is most likely addition elimination, because I have a leaving group and a strong withdrawing group and a not so great base in comparison. It's not NH2 minus, in other words. If it's NH2 minus, then I might think it's elimination addition. So now, what is going to happen? Well, the other reason why I'm saying this must be addition elimination is not just because I have those leaving groups and those withdrawing groups, but the positions of those groups relative to each other. If I look at this chlorine, I have a nitrogen that is ortho to it. And I also, or sorry, not nitrogen, but an NO2, a strong withdrawing group that's ortho to it. I also have another NO2 group that is para to it. Same deal here, I have a chlorine that's para to a strong withdrawing group, and here I have my chlorine para to still a withdrawing group, a weak one, but still a withdrawing group. So I'm very inclined to say this is addition elimination. So what happens during an addition elimination reaction? Well, you have, let's use this one right here. I'm going to draw out that ring and we're going to see what would happen. Now, I'm going to draw out the full structure of nitrogen, or NO2, which looks like this. A nitrogen that is positive, which has a single bond O minus and a double bond O on it. And it's on a benzene ring, and then we have the chlorine over here. Now what happens is that OH minus is going to come in and attack, and it's going to attack where your good leaving group is. NO2 is not a good leaving group, but Cl is. So this O minus is going to attack here. Now, the chlorine won't just come off, because things that are on double bonds have fairly strong bonds. This chlorine actually isn't such a great leaving group as it is right now, because you never really want to break the bond of a chlorine or a hydrogen or anything of that nature that's connected to a double bond. So what actually will happen is this double bond is going to resonate around. Nothing's getting kicked out yet. And the electrons end up resonating into the NO2. And so you get this intermediate right here, where now the nitrogen is still positive, but both of those oxygens are O minuses because this double bond resonated up into the oxygen. And now I have that nitrogen on a double bond to the benzene. Well, it's not really benzene anymore in this resonance structure, because what it'll look like is now the double bond is over here, and this double bond was never touched, and now we have a chlorine and an OH on the same carbon. So this is the intermediate you will typically get with an addition elimination reaction, because the nucleophile attacks the position where the leaving group is, and things resonate into the withdrawing group. And that is why you need that strong withdrawing group, typically in NO2, because you need this resonance to happen to get to this intermediate. If you don't have a withdrawing group that can resonate like that, well, it's not going to be so easy to make. So this is the key difference between 1 and 2. This is the key difference between 2 and 3. In 2, if this OH minus attacks the carbon with the chlorine, well, it can, and this will resonate up into the NO2. But here, we have a chlorine, 2 chlorines para to each other. So if that OH minus comes in and attacks here, and this tries to resonate around the ring, well, there's nowhere that this OH minus, when those electrons start resonating with the double bonds, you can't resonate into the chlorine, right? Chlorine can't resonate that way because it's got 1, 2, 3, 4, 5, 6 electrons, and it has 3 lone pairs, and then it's bond, so it has 8 electrons right now. You can't push the electrons up to the chlorine. So these electrons resonating from the benzene's double bonds can't go there, and so that's not so great. Which is the reason why 3 would be the worst. 3 is the worst again because you can't resonate the way an NO2 can with addition elimination reactions. Now, between 1 and 2, who is better? Probably the one with more resonance, because I'm forcing electrons in, and those electrons are a negative charge, right? Those electrons can either go to the NO2 here, like in 2, but then this one also has an NO2, and as long as the NO2 is in either the ortho or the para position to your leaving group, it can resonate. So, in the case of 1, we have 2 separate NO2s that you can resonate with. And so 1 would be significantly better than 2 for that reason, because the anion you make, the intermediate you make, is more stable. Now, as far as how does this reaction finish, just for completion's sake, the O-, one of those O- will swing back down, and the electrons are going to resonate, reforming the benzene, but now the chlorine gets kicked out. So your final product for each of these rings would be where the chlorine is replaced with the OH. So for 2's case, this would have been the final product. And with 1's case, it would just be this, but now there's an NO2 over here as well. So who is the best? 1 is the best, 2 is in the middle, and 3 is the worst because it can't afford any resonance to your intermediate. And so that gave you answer choice E. That's 3, 2, 1.